So I'm just going to recopy that transformer impedance here. ZAB equals R1, the resistance of the primary side, plus J omega L1, which is the reactance of the primary side, plus this term omega squared M squared over R squared plus J omega L2 plus ZL. These two just represent the reactance. We go look at our circuit model up here. That's just R1 plus J omega L1, right? So that's just what we would expect in the circuit model, from the circuit model. But then we see that the impedance, as seen from the voltage source, has this extra term here, this omega squared M squared over R2 plus J omega L2 plus the ZL. And what this shows us is this is how the load influences the primary through this mutual inductance. This term here is called the reflected impedance. A lot of times it's given the label ZR, and it's called that because it's the equivalent impedance of the secondary coil and load impedance transmitted, or sometimes said reflected, to the primary side of the transformer. This reflected impedance is due solely to the existence of mutual inductance. Therefore, if the coils were for any reason decoupled, meaning M became zero, this whole ZR term would become zero, right? The M would drop out. The M would cause that thing to go to zero. And then ZAB, the whole thing would just reduce down to the self-impedance of the primary coil. So we call that the ZR is equal to the reflected impedance. So let's go ahead and put that in terms of an example. So we're going to have the following circuit. We've got a primary side of a transformer that's connected to a 300 volt voltage source. This voltage source has an internal resistance of 500 ohms, and it has a internal reactance of J 100 ohms. It then has the transformer itself. The transformer has a internal resistance of the primary of 200 ohms, and the self impedance of the primary of J 3600 ohms. There is the secondary, which has a secondary self-impedance of J 1600 ohms and a secondary series resistance of 100 ohms, and that is feeding a load that is an RC load. It's got 800 ohms of resistance, and the capacitor looks like a 2500 ohm resistor at the frequency of operation. Additionally, there's 1200 ohms of mutual inductance at the frequency of operation in this circuit. So the first thing that we want to do is calculate the self-impedance of the primary circuit. So remember, self-impedance is Z11 that's just going to be equal to 500 for the resistor, plus J100 plus 200 plus J3600, and that gives us J3000 is equal to 700 plus J3700 ohms. Next, what we want to do, I'm going to just add a little space here, we want to calculate the self-impedance of the secondary. So that's Z22. That's just going to be 100 ohms plus J1600 ohms plus 800 ohms minus J 2500. And that's going to give us a self-impedance of the secondary circuit of 900 minus J 900 ohms. We now want to calculate the impedance reflected into the primary winding, that's ZR, the reflected impedance. We see that's omega squared M squared over R squared plus J omega L2 plus ZL. So omega M was already given to us as 1200. So we get 1200 squared. We then need R2 plus J omega L2 plus ZL. It's 100 plus J 1600. Oh, it's actually this 900 minus J 900, right? And that's going to give us a value of 800 plus J 800. So next I want to calculate the impedance seen looking into the primary terminals of the transformer. That's just going to be the impedance of the primary windings plus the reflected impedance. So ZAB is going to be equal to 200 plus J 3600, those two terms there, plus 800 plus J 800 ohms, and that gives us, 800 plus 200 is 1000, and 800 plus 3600 is J 4400. So that gives us the impedance seen looking into the primary terminals of the transformer. That kind of characterizes the impedance of that circuit there. So we'll stop with that for right now.